Well, thank you very much. Woo. Well, I'd like to start by first thanking Nana and Beth and TSRC. This is certainly a fantastic opportunity for scientists to come here. And really the town as well. I mean, I'm really, really grateful that you share this beautiful town with us. And like Beth said, we've been coming for many years, and I think we'll continue to do that essentially indefinitely. So what I want to talk about today is from atoms on up, designing better batteries and fuel cell catalysts. And it's really very general about how to design new materials. And what I want to try to convince you of in this talk is that we're really at the start of a revolution. This has only been possible in the last 5 years or so. And I'll say a little more what I mean about that. By designing from atoms on up, I really mean computationally. So not designing in the sense of trial and error, which is the traditional way of doing it. You make a new material, see how it performs, try, which I'll try to show you takes a very long time. This is a different sort of approach where you decide what sort of property you want, and you put the atoms where you want on the computer, and you design a material that way. And I want to give you two examples from my own research lab, which are very modest. One of them is about battery materials, the other one's about fuel cell catalysts. And the things we've discovered are not going to revolutionize, the energy landscape of this country by any means. But what I think is really exciting here is that it's an example of where we have really designed something on a computer, and then synthetic people, my collaborators, have made the materials and seen that they work the way we expect they work. And that's, I think, what's revolutionary and really exciting. Let me start by giving a little motivation. So as Beth mentioned, we need things better and cheaper, particularly when it comes to energy, and that's my interest. So, as one example, I know Telluride's very interested in solar cells. I see them up around the town, and I think there's a project to power the gondola, which is great. But conventional silicon cells are still very expensive. These are single crystals, they're difficult to make, and they capture only about 12% of the sunlight. And so if you look at the cost of these materials, it's about $20 per watt, which is far more than a conventional energy source like coal. And even personally, even though I really am in favor of these cells, when I look at putting them on our roof in Austin, it's a big, it's going to be $20,000 or something, and it's going to pay back over 25 years. So it's still pretty marginal. And if these things were twice as efficient and half the cost, I think they would be, really big. People would be putting them up all over. Fuel cells is something else I'm going to talk about. So, traditionally, when you have a car, for example, and you put fuel in, you burn it in a combustion engine. And that's relatively inefficient, maybe 20% at most. You can do much better if you burn them, in a sense, chemically. So you combine your fuel and oxygen together, and you can get up to about 70 or 80% efficient. Unfortunately, what you need to do this is what's called a catalyst. That's what makes the reaction happen quickly. And the best catalyst for that is platinum. And so if you make a fuel cell here, yeah, platinum, right. It's sad that it's so precious. But the cost of a fuel cell, this is just a concept vehicle, is about $100,000. So again, if we could make the catalyst twice as efficient and half the price and get this down to $25,000, we'd kind of be in the range of what would be feasible. One last example, an all-electric battery car. This is something that I would love to have. But the current technology is just a little bit low in capacity. So the Nissan Leaf has a 75-mile range. You'd really like that to be a couple hundred. Certainly when we drive from Austin to Telluride, this would be a real limitation. The charging time is a little bit slow, and the cost of the battery pack adds significantly to the cost of the car. I mean, it's really outside our price range. And what I want to convince you of here, or tell you, is that in every case, what we need to do to make these better is these materials. Semiconductors here, precious metals, metal oxides is what stores the lithium in these cells. And so if we can design better materials, we can make a big impact on the way we use energy. So I mentioned that traditional discovery, this sort of trial and error discovery of materials, is slow. And I'll give you an example which is actually tremendously successful. I mean, this is really one of the best positive examples of trial and error. And that's the lithium-ion battery, which is, of course, ubiquitous now. So it was developed by a guy I'll mention, actually, John Goodenough at UTAustin in the 1970s. This is when they first came up with the lithium battery. And it took about 15 years until these batteries were commercialized in laptops. And the primary material they used, this is the material that soaks up the lithium when you're discharging your battery, was lithium cobalt oxide. And it's not a bad material, but it has some problems. For one thing, cobalt is not a very nice metal. It's not the kind of thing you want in your environment. It's kind of expensive. And also the oxygen here can be released from the material, which can cause batteries to burn. And if you Google on YouTube, you can see lots of cases. I don't want to discourage you. I mean, they've made lots of progress. They're not going to be burning. But it's particularly when you have a fast charge and discharge like you'd want in a car, you really run some risk. So these are not really used. These are not applicable for car applications. Okay, in 1996, the same guy, John Goodenough, I mean, this is an amazing guy. He can just design these things almost in his head. Developed a new material called iron phosphate, which has a lot of advantages over this cobalt oxide material in that it's basically a rock. These are all earth-abundant materials. It really does look like a rock. It's very stable. It will never burn. But it has some limitations. The lithium is very slow to go in and out of the battery. So it needed some work, and this is where the trial and error came in. So 5 years later, they had a startup company that started to produce them. And then about 5 years after that, they started selling the first commercial batteries. And because they're low power, these were powering Segways, actually, those those stand-up carts that you ride on. And also, I mean, I think I bought a drill this year, which was a lithium-ion battery. So they're starting to be used. And then another 5 years later, they were starting to be showing up in the first cars. This is a Fisker car. So you can see, again, it was about 15 years here between when something was discovered and when it was finally in use. And just last year, this is John Goodenough here with the president getting the National Medal of Science for this. So it was a very positive story in the sense that there was a lot of good development, but it's slow. And that's the kind of thing we want to speed up with our computational techniques. So we want to use computers for material discovery. And of course, we all know that computers are getting much, much faster over time. So if you think about a typical computer that you would have, the government has invested lots of money into big computers for us to do calculations on. So about 1 million times more powerful than your own computer. This is one that was just built in Texas, just north in Austin, by the National Science Foundation. The Department of Energy built one that was very similar. So we really have a huge amount of computational power. I mean, you might think there's just no problem. We could calculate anything. Unfortunately, nature is not so nice to us, particularly when we're interested in these materials that have electrons. In fact, everything that makes these materials work that I discussed involves electrons moving around. That's what chemistry is all about, is how electrons move. And the laws of chemistry are very different than the laws we're familiar with, the so-called classical laws. And I just want to try to very roughly describe what makes these laws so painfully difficult to deal with. So imagine we're talking about something like a baseball, and you just want to describe the position of a baseball. And imagine it's just on a line. And you just want to say where that baseball is sitting. Well, classically, in classical mechanics, you just have to give one number. You just say it's 1 meter along this line. It's sitting there. Quantum mechanics, when you want to describe where an electron is, it actually doesn't sit in any one place. Quantum mechanics is a little bit fuzzy. You have to describe a probability, or actually a wave function, that describes where this electron is. And so you'd need many points to describe this shape of this wave function. Still, not that bad, right? This might be 10 times as hard to describe as that one. But then when you think about describing this in 2 dimensions, well, your baseball, so a baseball might be on a field. It would have some position in X and some position in Y. No problem, 2 numbers. But when you want to describe your electron, now you need 10 by 10, 100 numbers. So the problem has gotten a lot worse here. And you can see how this is going to scale up. In 3 dimensions, you need now 1,000 numbers. And of course, we're interested in much bigger systems. We want a system like this is a hydrogen molecule that have 2 electrons, all in 3-dimensional space. And so we would need something like 10 to the 6 numbers here, 1 million. It's still tractable, but we're not really interested in H2. Let's say oxygen, that's something we're going to care about. 10 to the 30, I mean, this is basically almost impossible. And the thing I want to talk about is like a metal particle with oxygen dissociating on it. 1,000 electrons. I mean, this is more than the number of atoms in the universe. You really cannot just solve quantum mechanics directly. It's a great simple theory, but completely intractable as far as just solving it directly. So what has really made this all work, and the reason that we can do these sort of calculations that I'll describe, is a theory called density functional theory, which was developed 30 or so years ago by Walter Kohn here. He got the Nobel Prize in 1990. And basically his idea was this wave function is just impossible to deal with. And so instead of talking about a wave function, which describes the position of the first electron and the second electron and so on, we can just switch and talk about the electron density, which describes just probabilistically where the electrons might be. So to give you an analogy, like if we're going to talk about the state of the theater here, we might say, we have Jim in the first seat and then Joan. It describes everyone individually. That's this sort of complex description. Whereas if we just talk about density, we could say, well, the first row is 80% filled. It's a much simpler description, and it's not perfect. It doesn't capture all the physics, but it's so much simpler to work with that basically all calculations of the type I'm going to talk about are based upon this approximation. And this is really much more important than the development of the powerful computers that we have. So as I think, I'm not sure he exactly said this, but it's certainly a quote I've heard, that you'd much rather have this better theory with these old computers from the 70s than the new computers you have and the old theory. That's really how important this new theory is. Okay, I'll go to my two examples now. And the first one I want to talk about is catalysts and fuel cells. So if you remember, this is where you can mix fuels together, so say hydrogen and oxygen, and burn them chemically. So there's no actual burning, but they just combine and form water and give you electricity. And as I mentioned, the best catalyst for that is platinum. But if you look at the abundance, this is how much you find of something, and these are all the different elements. Platinum is sitting way down at the bottom. I mean, orders of magnitude less abundant than the more common metals that we're familiar with. And that, of course, makes it ridiculously expensive. So per troy ounce is about $2,000. So not only are these cars very expensive to make if you want to make a fuel cell car, it's actually, I've heard it estimated that there's not even enough platinum in the crust of the Earth to power our current vehicles. We really need something different and better, something that's more efficient. And actually, there's a performance issue as well. So if you burn hydrogen, you would ideally expect to get a battery that gave you 1.2 volts. And instead, you get something that's about 30% less. So if we can do even better than platinum, that would also be great, because then we could use less of it and reduce the cost. So before I describe what the calculation, let me just say a tiny bit about catalysis and how it works, kind of a simplified view. So this is our fuel cell. This is air coming in and our fuel coming in. And they're going to combine together to give water here and electricity. And what we're going to focus on is where all the action happens, where these chemicals combine with each other. And what I'm drawing here is an energy landscape. In fact, almost every conference I come to in Telluride involves energy landscapes. And it's completely suitable because we always have the mountains to talk about. So we talk about climbing up to the peaks and down in the valleys. So that's gravitational energy. When you climb up a mountain, that's what you're fighting. Here, molecules, when they cross hills, they're fighting chemical energy, but really it's the same thing. If you have to cross a high hill, that's a lot of work. So here's our reactants, the hydrogen and the oxygen, and this is what we want to get out, water and electricity. So the best case we could have is just like a flat energy landscape, just walk along a boardwalk. It'd be perfect. But of course we have chemistry, so these molecules come and they sit on a surface and they break bonds, and so you have to cross these hills and you get a rough landscape. And there's two kinds of extremes you can think about. If you tried to use something like gold as a catalyst, you probably all know intuitively that gold is going to be a very bad catalyst because things don't react with it. You have a gold ring. The reason you use gold is because it stays gold. Nothing reacts. It doesn't oxidize. So particularly I'm thinking about here reacting with oxygen. And what that means in terms of an energy landscape is that you have very high barriers to climb. So that's a bad case, using gold. You could say, well, let's use something that interacts more strongly with oxygen, iron. It's spontaneous there. You have very low barriers. Oxygen will just stick to iron. In fact, it rusts, right? You put iron out and it rusts. The problem with that sort as a catalyst, though, although the barriers are low, you have these deep valleys. Oxygen sticks there and never leaves. So, a rusty catalyst isn't going to be any good. So this is the compromise I'm talking about. It's just as bad getting out of a valley as it is going over a big hill. And we have to have a compromise between these two to get the flattest overall energy landscape that we can. And so if we think about all the different kinds of metals that you could have, these are the ones that react too strongly with oxygen. They oxidize iron, cobalt, all these nasty things. They have the deep valleys. And the activity that's plotted here, so this is how well they work as a catalyst, is very low. In the other extreme, gold and silver, they also have very low activity because their barriers are too high. And this here is what's called a volcano plot. So the activity is going to be peaked at one point, which is at some particular interaction strength of oxygen with the metal. And you can see that platinum here is very near the top. So we could do a little bit better than platinum, but in terms of pure metals, this is the best we can do. And the reason this is called a volcano plot is because this is where all the activity is. That's the highest activity. That's where we want to be sitting. So in terms of our calculations, this is what we can focus on. We can look at different materials and find one that interacts with oxygen with this sort of strength, and that will give us the best activity, at least in theory. So this is the calculation that we did in my lab that my students did. We considered a small little nanoparticle that has a shell of platinum, and we considered putting different metals on the inside of this that can change its interaction with oxygen. And we took two extremes, one where we put in a gold core into this particle, and this binds oxygen too strongly. And then we put in palladium, and this binds oxygen too weakly. And the nice thing about that is then we can make an alloy. We can mix the two together and get right to our target binding energy. So it's like we have a way of tuning this to be just perfect. And if we do that, we find that the optimal should be 60 or 76% platinum, basically 3 atoms of platinum to 1 atom of gold. So that's our prediction of an optimal catalyst. So we have a synthetic collaborator at UTAustin, Dick Crooks, who's able to make this. And the way he makes it is not very important, but he takes metal salts and they go into solution with a very branched molecule, and then he reduces them into a metal particle. And he can do this with 2 types of metals to make an alloy core, and then he can do it again to put a shell on top of it, and he can make exactly the kind of particle that we calculated. And when he does this, and this is kind of the punchline for the story, this is the activity as a function of the composition of palladium in the core, and the best catalyst here is just what we predicted to be, 75% palladium in the core. And you can see it's better than platinum. So that's one success for it, something where we predicted it, we convinced our experimental colleagues to make it, and it turned out to be the way we expected. The second short example I'll give you is on these lithium battery materials, and the material I'm going to talk about is the same one I mentioned before, this iron phosphate. And I mentioned that it's a little bit slow to take up lithium. There's something that prevents the lithium to go inside of it. If it would go inside faster and get out faster, it'd be much better for cars, because when you put the accelerator down, you really need a lot of electrons to flow quickly. And similarly, when you want to charge it, you don't want to be waiting 8 hours. Something like 4 hours would be, or 2 hours would be much, much better. And so there's a lot of work in trying to figure out how to take this very stable, cheap material and make it work better. And so we did a similar kind of calculation to what I described before. And what I'm showing here is one of these energy landscapes. And it's the same kind of thing. We want this landscape to be as flat as possible. Any hills we have to climb are going to make it harder for the lithium to move in and out of the material. And the calculation here, this is the material, and this is the surface of the material, and this is lithium in the material. This is the electron that's associated with the lithium. So lithium is actually an ion, so I call it a lithium-ion battery. And the electron sits on a neighboring iron atom. And this is the energy as we're going to go up to the surface. And so if the electron moves here to this next site, the energy is about the same. And then once it gets to the surface, the energy goes up a lot. And the reason for that is that the electron is sitting on this iron atom on the surface. And it's very unhappy there. The iron is not well coordinated. It's on the surface. And so the electron is unstable there. And so once we had seen this in our calculation, then we could target a change. We could try to stabilize this electron. And our idea was that we could take one of the oxygen atoms next to the iron and switch it one over in the periodic table so that the element would have one less electron, and then it would be happy to take up another one. And the guy who's one over from that is nitrogen. So we took this oxygen. Oh, there it is on the surface. Wait, I'm getting ahead of myself. So here it is swapping with nitrogen, and you can see the electron moved from the iron to the nitrogen, and the energy dropped a whole lot. And so we got rid of this extra barrier, and that means lithium is going to go into and out of this material more quickly. That's our prediction. So in collaboration with John Goodenough's group, they made these particles and they put them in ammonia, which puts nitrogen on the surface. And you can see, and the details are not that important here, but this is capacity, how much lithium you can get in as a function of the voltage. And there's an improvement about by 20% or so due to this nitrogen on the surface. So like I say, this is not going to revolutionize the batteries in cars. We don't have a factor of 2 here. But it's certainly a big step forward, I think, because of the procedure, the fact that we're able to design it on a computer and then reduce the amount of time it takes to improve these materials. I want to say that I'm not the only one doing this kind of thing. And I think that's what's particularly exciting about this, is that there's a lot of momentum behind this. There's a lot of people who realize that this is going to be important. So 2 years ago, Barack Obama announced that there's going to be the Materials Genome Initiative. So it's kind of like you think of a genome for the body. It's the code the genetic code that gives us all our characteristics. And so it's the same idea that you could do that with materials as well. If you know where all the atoms are, then you can predict the properties, and perhaps you can change the code or where the atoms are and make better materials. And he says exactly what I've been saying, that we want to increase the development time of new materials. There's a fantastic project, which is at a collaboration between different universities, Berkeley, MIT, the Department of Energy. And here, this is related to batteries, where they've screened a huge number of batteries materials. Of course, computers are very good at that, right? You can try any number of materials and look for ones that are particularly good in terms of safety. This is what I mentioned in terms of some materials losing oxygen, and the voltage, how much energy you're going to get out of it. So it's just looking across all the materials we could think of and trying to find ones that are particularly good for batteries. Another final one I wanted to mention is at Harvard. This is trying to look for better solar cells. So instead of this expensive crystalline silicon cells that are used now, the idea is to try to find things that are more like plastics. So you can print them, make them very cheap, put them as coatings on windows, for example. So I think these are all very exciting. And actually, this one here has a distributed computing element to it. So if you go and Google for this on the web, you can have your computer search different molecules and do these quantum calculations and see how efficient they will be for capturing sunlight. So the future is bright, and let me just finish by showing my group. These are all the young people who are going to take this project into the future. And with that, I'll thank you and turn the microphone over. I guess questions are later. So, thank you very much.
I just discovered something about Graeme and I, another coincidence being Canadians. He did his undergraduate in physics at the same university as I did, Queen's University in Kingston, Ontario. And Queen's University was a Scottish-based engineering university, and if you did your studies in physics, you were in the science faculty. You were called science. And if you did your physics studies from pure physics, you were in the arts faculty. Well, it's my pleasure to talk to you today about the changing polar environment. I'm going to focus particularly on the Arctic and use the Antarctic as a contrast, just a little spice. And also challenge you to think from the point of view of changing environments as threats or opportunities. I'm not going to offer any judgments except one at the end. And I'm going to leave it up to you to make your own opinions on the facts. Let me just, I don't think, I just need a pointer here. Okay, got a pointer. Let me start by a nice picture of the two poles, contrasting poles. The Antarctic, to begin with, is a dome of ice. It's about 4 kilometers in altitude, 12,000 feet or so, 14,000 feet. And it stretches out to 60 degrees, okay, roughly, from the pole, 60 degrees latitude. It's surrounded by an ocean with winds, the roaring 40 wind belt. It's relatively clean as far as being in the southern hemisphere. In contrast, the northern polar region is centered on an ocean, the Arctic Ocean, surrounded by continents. And also it has some very interesting obstructive topography as you go around the circle. You hit the Rocky Mountains, then you hit a 2.3 kilometer or 2,300 meter. What's that? I've been away from North America for so long, but 7,500 feet high, Greenland, and maybe the Norwegian mountains and the Caucasus. So there's lots of mountains. This ocean is called the Mediterranean of the North because it has basically one major exchange route for water in and out. A little bit trickles out the Canadian archipelago, a little bit trickles in the Bering Strait, but most of it comes in and out this area. And you get some fresh water inflow from the big rivers, the Mackenzie and all the Russian rivers. But what's interesting in the contrast between these two from the air quality and the atmospheric chemistry point of view is that these populated continents have a lot of pollution, a lot of emissions of pollutants to the air. And I just put this up to summarize the issues that drove our awareness of the polar regions to some extent historically. When I first started in the game, Beth mentioned acid rain. The Europeans the Scandinavians were starting to sue the Germany and the UK for polluting their lakes with acidity and killing trout. And then Canada and the US took up the dialogue, and there was two regional dialogues that ended in treaties and controls. And that was viewed as that first of all raised public awareness of the regional scale long-range transport of pollutant. But we started making measurements in the Arctic about the end of the 1970s. First at Barrow, Alaska, by a professor from University of Rhode Island, Ken Ron, and then a consortium, myself and the Canadian Arctic and the Norwegians, and we discovered that remnant acid rain was moving into the Arctic in the winter. And it was coming in from, this is the sulfur dioxide emissions in the late in about 1990. This is gridded emissions. Blacker it is, the higher it is. Around eastern North America, big source, Eurasia, and the China just developing at that time. And so what are the atmospheric pathways into the Arctic region from these sources? Well, we did a lot of detective work using meteorological models, just generally a lot of observations showing concentrations higher over on this side and moving in. And we discovered that the main pathways of the eastern North American emissions were out over the Atlantic Ocean, where it's really rainy and stormy and cuts off and scavenges most of the pollution before it gets anywhere. There is a little backflow here, but it's not very great. Whereas Europe, in the winter months, is well connected with no waterway, no stormy areas with the Arctic. And so Eurasia turns out, and later on a little bit of China at the end of the winter, to be the major source of this pollution into the Arctic. And this is a lower atmospheric circulation pattern I'm showing you. In the winter, the Siberian high pressure builds up massively. And around the high pressure, the flow is always clockwise. And low pressure is coming off the Atlantic. It's always anti-clockwise. So every time a low pressure rippled into Europe, you get a big pulse or plume of pollution into the Arctic. And there's very little precipitation in the Arctic in the winter months. So things are long-lived. So these plumes just accumulate and puddle up. And so you get a pattern that when I first established a sampler at Alert here, 82.5 degrees north on Ellesmere Island in Canada, we measured sulfate, which is a particulate product of the oxidation of sulfur dioxide. We saw this phenomena. And we saw this at many other sites throughout the Arctic, Mold Bay, Glue Lake, Barrow, Svalbard over in... and in the winter months, the Arctic is November to May, much more polluted with this sulfur aerosol than in the summer. When the pathways aren't so good, things get scavenged by a wet, cloudy Arctic. If you don't believe me, I'll show you just a picture here from New-Olison over on the European side. There are two days where you have clean air transport from the North Atlantic and then transport up out of Europe. And very, very different phenomena, visibility reducing, and so on. We've been, since that time, developing globally a very large network of observational platforms. One of my jobs for 9 years was as research director at the World Meteorological Organization in Geneva, I was in charge of the Global Atmosphere Watch program. And that was to coordinate global observations of greenhouse gases, aerosols, ozone, and so on. And we used ground-based observatories like this one at Alert, this one run by NOAA at South Pole. There's many of them run by NOAA. The Japan Airlines commercial aircraft flying with CO2 sensors. There's now a whole in-service aircraft program with Airbus that I'm involved with, measuring atmospheric composition. There's satellites measuring all sorts of things. There's only 2 measuring greenhouse gases right now of any significance. And then we have ship-borne platforms. And I tell you this because, and this is also more closer to home, the ground-based network for greenhouse gases. This is ship tracks, but all the rest are the surface-based sites. About 70% of these are run out of a program in Boulder, the Global Monitoring Division of NOAA. So it's been a mainstay of the global observing system since they took over. Actually, even Mauna Loa is run by NOAA, from Charles Keeling, the famous one, who has the longest CO2 record. Now, from such observations, and from sampling glacial ice cores, which happen to, after 70 meters, form solid ice and trap air in bubbles, so that it remains. If the gas is inert, you actually trap the atmosphere, and then you can recover it and measure CO2. Let's go back 800,000 years. And we can start now. We have the highest concentrations in 800,000 years that we've ever seen. Okay? Unprecedented, up to 400. This is expanded here for the last, since 1700, since Peter the Great, okay, took over, French Revolution, around in here. And this is the instrumental record presently for carbon dioxide. As you go back, carbon dioxide decreased, but as you went back into a glacial maximum, carbon dioxide in the atmosphere increased because the land and the ocean didn't have the capability of drawing it down as it was released from the surface. So there's a cycle here through each glacial period. And you go back, but throughout the 800,000 years, we've never seen a concentration higher than roughly 280 parts per billion. That's 280 molecules per billion molecules of air. Okay? And so we're in an unprecedented regime, at least for the last 800,000 years. And CO2 is a greenhouse gas. Its solar radiation comes in, the Earth re-emits a longer wave infrared, and CO2, the vibrating molecule, absorbs it and re-emits it partially to the surface. And so we have a warmer surface than if it had not been there. So that's the greenhouse effect. Methane is also an important greenhouse gas, Ozone 2O, and some of the chlorofluorocarbons that we're using in our refrigerators and have used. Speaking of chlorofluorocarbons, I'd like to also talk about ozone, and this is turning now to my second career interest. Ozone comes in different flavors. There's good ozone, which is the most abundant in the atmosphere, in the stratosphere. We have the stratosphere, which is above about 14 kilometers. In the polar regions, it's down to 8 kilometers, so it's like this, slopes towards the poles. The ozone in the stratosphere absorbs ultraviolet radiation and protects us. If you use spray can propellants of HCFCs, you get up here, there's plenty of UV. These fluoride, chloride, bromide compounds, they photolize in the UV, which is ozone scatters it out down below, but once they get high enough, they photolize and release chlorine bromine, and there's a big chunk taken out of the ozone through catalytic reactions. We talked about catalysts in the solid state. We have them in the atmosphere in the gas state. So this ozone layer was causing a real problem, and many of you perhaps heard of the success of the Vienna Convention in 1985 to control spray can propellants and replace HFCs with shorter-lived HFCs, CFCs with HFCs. Now, second flavor of ozone is the ozone in the in the troposphere, which can act like a greenhouse gas. And this ozone is leaking down from the stratosphere, but also formed from chemistry in the troposphere. And the group that's meeting here this week are a bunch of atmospheric chemists and surface ice and biochemists and ocean chemists and biochemists. And we're all interested in ozone and what it does down here. Now, in urban areas, the third kind is photochemically produced ozone, which nitrogen oxides and volatile organic compounds from tailpipes react in sunlight to produce ozone. But in the Arctic, we can also have, as we had discovered in 1985, ozone destruction at the ground due to halogens released from sea salt on the Arctic Ocean. So you've got chloride, bromide, not in spray can propellant sort of gases, but on the surface. And we discovered there was a bromine explosion that was destroying ozone. And that has many implications. But ozone is a greenhouse gas, and it's being produced by chemistry from pollution in the atmosphere. And we know that this free tropospheric ozone has gone up from around 10 to 20 parts per billion. These are from ground observatories or high mountain observatory, all the way up here to sort of these free tropospheric values of anywhere in the range 40 to 60. And that has implications for the greenhouse effect, which were nicely and popularly represented, assessed by NASA in a global model. And you can read it for yourself. They basically showed that free tropospheric ozone is contributing substantially in the Arctic to the greenhouse effect. Okay? Now, when you put greenhouse gases together in the atmosphere with black carbon, which is again from the tailpipe, poorly combusted fossil fuels, or from poorly combusted coal in in thermal generating stations, such as in China, former East Bloc Europe, and you get a warming effect generally in the atmosphere. Aerosols, also, these sulfate aerosols, they're not black. They scatter light back to Earth. If they scatter sunlight out back, and if they're over a dark surface, they make it whiter. If they're over a white surface, they don't make it quite so white, so they don't have this big effect. Black carbon, on the other hand, has a big effect. So the polar regions likes black carbon as a warming agent. Okay, so it contributes. When you put this into global models, which was in the Intergovernmental Panel for Climate Change, founded in the late 1980s, as an assessment process that runs every 6 years, collecting the knowledge of science, shows that the Arctic, from the global perspective, there's a global projected, there is an observed globally increase in temperature since the mid-1800s of about 0.9 degrees. But in the polar regions, it's much more, projected by models, a polar amplification process. And every model agrees. What's happened in the last 30 years? The models predicted something. What about observations? Yes, again, we've seen the most warming anywhere on the globe, except perhaps a few spots down here, in the polar region. Okay? And how does this manifest itself? We observe it in the temperature record. But lately, there has been a dramatic change in the Arctic Ocean ice. Here is the limit of ice in September 2012 in the Arctic Ocean. observed from satellite. The yellow line is the mean limit between 79 and 2010. This is dramatic change. But even more so, and I'll just show you a slightly different linear plot of this surface area covered by the ice at its the ice extent at the minimum in September. And you can see the time series marching along. Get rid of this linear line. I like to look at it like this. Boom. And 2012 was the all-time low. What more dramatic, in my mind, even at its maximum, this is an assessment of the first year. What flavor of ice do we have in the ice in the Arctic at the maximum ice extent of the coldest part of winter? Blue is first year ice. The next color is second. Third is green. Fourth is yellow, and fifth is red. And you can see that the 5-year-old ice in '85 constitutes roughly 20% of the area, okay, or even more. And now it's down to less than 5%. And a huge portion of the Arctic has only first-year ice. It's like southern lakes, and this has huge implications for many things. Let me just say a few things about some wild cards with respect to this amplification. If the temperatures are increasing in the north and things are warming, not only the Arctic Ocean, the carbon-rich tundra, the permafrost has a lot of carbon in it. And if it melts, there's going to be carbon released and carbon dioxide feedback. So there's a positive feedback on the increase of CO2 being driven by fossil fuel combustion. We also have an interesting side impact here of the warming. There is, and I'll say it right now, it's a hypothesis that's being tested by the scientists around the world, that in the last 5 years since we've experienced decreased ice cover in the Arctic Ocean in the summer, there has been shifts in weather patterns which lead us to believe that there have been slightly more severe winters in the eastern part of the U.S. and Canada. This comes from NOAA, so it's the U.S., but I'm sure Canada and parts of the central along the border have the same in heavier winter, and the same thing in Asia. So there's a warming pole leads to more severe winters in the south. That's global warming. That's the dilemma of it. Our biologists, marine biologists, friends, ask the question, what's the impact of the warming Arctic? Of course, we have these macrobiota, as Patty Matrai in our group likes to call it. Polar bears, lovely creatures, many creatures, but the perhaps more explosive threat is for the charismatic microflora, as Patty labels them, that sustain the food chain for these creatures. And there are subtle and very serious impacts occurring that we're just starting to begin to understand because of the shift in ice regime and temperature regime. Okay? And to quote Patty, that the ecosystems are looking for a new equilibrium. Maybe they can catch up. Maybe it's going to change too fast. But we don't know how this is going to affect them and currently the spectrum of fauna and flora that live in the Arctic. What's this funny picture? I put this up because it's a well constructed, based on all great research and knowledge of fossil fuel combustion, of the nitrogen oxide emissions from tailpipes and internal combustion engine exhaust throughout the greater European region. Okay, you can recognize here's the UK and here's Spain, and this is down through. Here's the Suez Canal, and what I wanted to show you and emphasize that the shipping routes are very prominent with this, and you can see that there's a very popular shipping route that comes through the Suez Canal from Asia all the way over to here. And there's also one that runs up to Murmansk, but doesn't go any further over here because there's too much ice. There was. This isn't. What's going to happen now with the changing ice is this route across the north of Russia is going to be much easier to navigate. And the Chinese, for instance, are investing a lot in research and positioning because there's a 30% decrease in the transit time to European markets through this route from Russia, if you look at a globe. Also, there's possibilities of a Northwest Passage, although this is a messier part of the Arctic, but icebreakers are being built. There is going to be a lot more traffic from transport. There's oil and oil exploration going on throughout the Arctic. So there's a lot of shifts. So in summary, I'm coming to an end now. I would just like to summarize by saying that the Arctic will probably experience greater temperature change. The projections for the ice to be completely gone from the Arctic, except for a little bit around Ellesmere Island, is around anywhere from 2050 to 2040 to 2060. This is going to change the world tremendously. It is once a threat. Some people look at it as an opportunity. Okay, because of the delicate nature of the Arctic, things don't recover very fast. Anybody who's driven a vehicle in Arctic tundra knows that those tracks stay there forever. The food chains are very much simpler and more delicate. There's all sorts of sensitivities, and we need to treat this as a big part and tread carefully into it as we extract the resources. So with that, I'd like to thank you, and happy to entertain with Graeme questions.